Hello everyone, I am Ahmad, a PhD student at the Olives Lab at Georgia Tech. In this video, I will briefly talk over my work recently accepted to be presented at the ICIP 21 annual meeting. Deep learning has become a critical component of our day-to-day lives, from helping autonomous vehicles understand scenes and navigate around traffic to helping doctors and radiologists detect and diagnose complicated diseases to leading groundbreaking advancements in speech translation. A major requirement for many modern deep learning solutions is to have large quantities of labeled training data to allow the algorithms to perform robustly under a variety of different conditions. In several application domains, however, acquiring sufficient quantities of training data is limited by several factors, including but not limited to the cost and time of labeling needed, the fact that it has to be done by experts with sufficient knowledge of the domain area, the subjectivity of the annotations from one labeler to another, and proprietary issues restricting the access to data for the public. Performing interpretation on migrated seismic volumes is one such application. Migrated seismic volumes exist as 3D data carrying information about the layers and structures in the Earth. Identifying such structures plays a critical role in decision-making processes for oil and gas exploration, production, and carbon storage purposes. For many reasons mentioned earlier, annotating seismic volumes section by section by experienced seismic interpreters for automation by deep learning-based solutions can be a difficult, costly, and time-consuming task. Fortunately, we now know that not all training examples are equally informative for deep neural networks. Rather, some training examples carry more information compared to others. Consider a hypothetical scenario where you're given an object classification dataset consisting of only cat images, whereas the test dataset also contains other object categories. Now, regardless of how many cat examples you train the network on, it is unlikely to generalize to, say, dogs or cushions. In fact, having a training dataset containing all the representative subsets in the test data would outperform our hypothetical training dataset, even if it is much smaller. What we show in our work is that it is possible to identify the most informative training samples in a dynamic fashion for the aforementioned application of seismic data interpretation. Towards this end, we utilize the manifold learning properties of a deep autoencoder. Autoencoders are networks designed to learn to reconstruct only the inputs in their training data distribution while doing much worse at reconstructing those not in the training distribution. This leads to the autoencoders implicitly learning the manifold of their training data distribution. Any training example sampled from this distribution would lie close to the manifold structure, while those from a different distribution would lie further away from the manifold. This gives us a systematic methodology to sequentially select training sections from within the seismic volume furthest away from the training manifold the network would have already learned up to that point. By sampling and annotating data in this manner, we are able to achieve high generalization performance at the interpretation task measured in terms of the mean intersection over union for segmentation. Comparing our proposed method to other sampling strategies employed in the literature shows superior performance gains under limited data conditions. If you're interested to know more about this work, I highly recommend you to attend our poster presentation at the virtual ICIP meeting. For access to our codes and other works by our lab, please scan the QR codes on the screen to take you to the relevant websites. I hope to see you all at the annual meeting. Until then, I wish you all good luck and goodbye.